Good morning. So I want to talk about spin-spin coupling in NMR spectroscopy, and we're going to get better at understanding it. And in the next lecture, then we'll use this to analyze stereochemistry. So to get started, if I want to give sort of a general, rule on spin-spin coupling or principle on spin-spin coupling, also called splitting, by the way. I think the way I would say this is that peaks are split by adjacent protons that are different. We'll call it into multiplets, into doublets and triplets and doublets of doublets and quartets and so forth. So let's for a moment imagine what the spectrum of chloroethane should look like. So you've got a methyl group in the molecule. You've got an ethyl group. You've got a methylene group. You've got a chlorine. Chlorine doesn't really have spin to it. It has a nuclear quadrupole, but for all intents and purposes, you can ignore chlorine spin. So we've got a methyl group, and we talked about chemical shift last time, and we said, well, a plain vanilla methyl group is at about 0.9 parts per million. Methyl group that's beta to an electron withdrawing substituent, in other words, not attached to an electron withdrawing substituent like methyl chloride, like chloromethane, it's going to be a little bit downfield, a couple of tenths of a ppm downfield of that position. So if we draw sort of a sketch of an NMR spectrum, we'd expect the methyl group to be maybe a hair downfield of 1 ppm, maybe 1.1 or 1.2 ppm. The methylene group is next to a chlorine. And we said normally an electron withdrawing substituent shifts you downfield by a couple of ppm to be right next to it. Methyl chloride is at, I think, 3.05 ppm instead of 0.9 ppm. It's a couple of ppm more downfield. Methylene groups are a little more downfield than methyl groups. I said maybe 1.3 to 1.5 would be a plain vanilla methylene group. So if you're next to an electron withdrawing substituent, you're going to be somewhere a little downfield of 3 parts per million. The methylene group, I think everyone at this level should be able to recognize. The methylene group would appear as a quartet, and the methyl group would appear as a triplet. And I'm going to try to draw things in the appropriate relative heights here. So our NMR spectrum, our proton NMR spectrum would look something like this. And to describe this compound, to describe chloromethane, and more general for any sort of an ethyl group, we could say that the CH3s split the CH2s. In other words, this group here, this peak, the quartet, is split by the methyl group. And we'd say that the CH2s split, I guess I'd say the CH2 here. So I would say split the CH3, well, I guess since I was doing plural, I'll do plural on this. In other words, this group here is a triplet because it sees, right, it's the methyl group, it sees the adjacent CH2 group. And if we're talking in general here, we'd say that the protons of the methyl group don't split each other. In other words, we said you had to have adjacent protons that are different. The protons on the methyl group don't split each other. Even though this hydrogen is adjacent 2 bonds away to this hydrogen, because these two hydrogens are the same, they don't split each other. And if we're going to continue with that idea, we'd say the CH2s do not split each other. And again, for the same reason, because the 2 hydrogens of the CH2 group are the same as each other. But I'm going to throw in a caveat to get more general, and that is, of course, except if they're not the same as each other, if they're different from each other. And they would be different from each other if they are diastereotopic, or to put it in simple terms, except if there's a chiral center in the molecule. Obviously, in chloroethane, there isn't a chiral center in the molecule, but in other molecules, there might be, and we will see one. All right, so continuing to sort of look at our chloroethane case, I want to see why we get a triplet. So here's our CH3 group, right? Our CH3 group gives rise to a peak, and that peak consists of 3 lines in a 1 to 2 to 1 ratio of intensities. We call that CH2 group a triplet. We call that peak a triplet. And the reason we have a triplet here is because the hydrogens of the adjacent CH2 group have spin to them. And if you are 2 or 3 or 1 bond away, for that matter, in the case of heteronuclear coupling, but if you're 2 bonds or 3 bonds away, then it's close enough that you can see the spins. And the spins make little magnets. So the CH2 group makes a little magnet from the electrons having spin, and that basically that magnetism is transmitted through the bonds by polarization of the electrons. So the CH2 can have both protons spin up. Remember, we said protons can be either spin up or spin down. They can be 1 proton spin up and 1 proton spin down. And there are 2 ways in which that can occur. Or they can both be spin down, and that is why we get 3 lines corresponding to the 3 spin states of the CH2 group, and it explains why those lines are in a 1 to 2 to 1 ratio. Yeah.
Could you tell which one is like the 2 down or 2 up?
You can, in fact. And if the coupling constant is what's called positive, then it would be the one that's more downfield. The line that's more downfield would correspond to that spin state. If it's the one that you would call spin with negative, well, you can't tell 1 spin up, 1 spin down. You can't tell which is which. But if they're both down, you can tell that. And in fact, if you go ahead, and there are various coupling experiments that allow you to see phases, One experiment becomes if you irradiate one of the lines of the triplet, you can see how it affects the quartet and vice versa, and you can see relationships. Another is through phase-sensitive COSY, but all of this goes beyond the scope of the course. All right, and as for our quartet, that's in a 1 to 3 to 3 to 1 ratio, so our CH2 group appears as a quartet. And we get a 1 to 2, 1 to 3 to 3 to 1 ratio because there's one way in which our CH3, our adjacent CH3, can be all spin up. There are 3 ways in which it can have 2 spins up and 1 spin down. There are 3 ways in which it can have 2 spins down and 1 spin up. And there's one way in which it can have all spin downs. In other words, statistically, of all of your many, many molecules, 1/8 of the molecules, roughly, have the CH3 with all 3 spins up. 3/8 have the CH3 with 1 spin up and with 2 spins up and 1 spin down. 3/8 have the CH3s with 2 spins down and 1 spin up, and 1/8 have the CH3s with both spins down. Thoughts? And so we can generalize this idea that in equal couplings, and I emphasize equal, meaning the same coupling constant, lead to n+1 lines. So for example, if we do 2-chloropropane, if we consider 2-chloropropane and we consider the methine group, the CH group, it has 6 equal couplings, so we get 7 lines. What we call a septet, and the septet is in 1 to 6 to 15 to 20 to 15 to 6. 6 to 1 ratio. Which means the outer lines of the septet are so small it's very easy to miss them. In general, of course, you can work out the statistics, or it falls on what's called Pascal's triangle. Pascal's triangle, you just go ahead and add the 2 numbers above, so you keep putting 1s and then you say 1 and 1 is 2. That gives you your statistics for the triplet. The quartet is 1 to 3 to 3 to 1. Now for a quintet, you go 1 to 4 to add 3 and 3 is 6, add 3 and 1 is 4 to 1, and so forth. Or you can just work out the statistics yourself by working out the combinations of spin up and spin down. All right, so let's take a look at another molecule here, and I'll take a look at the molecule valine. And so if we look at the methine that I've underlined in valine, if you had 8 equal couplings, you'd say it would be an octet. So it could be an octet. Or to put it more specifically, if the coupling constant, the measure of the coupling of the methine to the methyl groups, was the same as the coupling constant of the methine to the methine, then you would see an octet. Now, the coupling constant of a proton to an adjacent methyl group in an alkyl group is invariably about 7 Hertz. If the coupling constant between methynes was also 7 Hertz, then you would see an octet. In practice, that coupling constant's a little bigger. It's usually about 10 Hertz, depending on the conformation of the side chain. In that case, you have what's called a doublet of octets. So I'll say it may be an octet, or it may be more complicated, which in this case, as I said, would be a doublet of octets. Protons on heteroatoms are a little bit tricky because protons on oxygen often exchange rapidly. It takes a while to be able to see the spin. It takes some milliseconds. If the protons are swapping very rapidly, more than once a millisecond, you don't get coupling. So for a molecule like octanol, the OH, not octanol, I'm sorry, 2-propanol. The OH may or may not couple. Depending on how fast it exchanges. And indeed, I can give you conditions under which you will see coupling for a secondary alcohol, and I can give you conditions under which you will not see coupling, depending on how fast the exchange rate is. If I ran the spectrum in deutero-DMSO, I would expect to see coupling. If I ran it in chloroform that was wet and had acidic impurities, chloroform decomposes to give HCl, then I would expect to see it exchange. If I ran it in chloroform that was dry and acid-free, for example, passing the chloroform, deuterochloroform, CdCl3, through some alumina that I dried over a flame or a furnace, then I'd expect to see it not exchange. So it may be a doublet or it may be a singlet. And this CH here, in turn, coupling is mutual. So the CH, depending on whether the OH is coupling or not, the CH might be more complicated than a septet, or it might be a septet. If it's exchanging rapidly, it might be a septet. If it's exchanging slowly, in this case, I would expect this coupling constant, the CH to OH coupling constant, to be a little bit smaller. So I probably wouldn't see an octet. I would probably see a septet of doublets, which is which would result from 2 unequal coupling constants, 6 1 Hertz coupling constants, 6 7 Hertz coupling constants, and one that was a little bit smaller, maybe 5 Hertz. That's getting a little bit, I'm getting a little bit beyond where I want to go, and I'm going to come back to this concept of unequal couplings in just a moment, but we'll start with a simpler example. So I want to write out one idea right now, and that is the idea of what's called chemical equivalence, which is just a fancy way of saying whether two protons are the same. And so what I'm going to say is two protons are chemically equivalent in other words, they have a certain type of sameness if they are interchangeable by a symmetry operation or a rapid process. And by a rapid process, I mean, for example, rapid rotation about bonds. In general, for example, rotation of about a single bond is rapid. As a matter of fact, for the purposes of this course, I would say rotation about every single bond between sp3 hybridized atoms is rapid on the NMR timescale. So if I want to then amplify on chemical equivalence, I'll say chemically equivalent protons have the same chemical shift and don't split each other. In other words, two chemically equivalent protons are the same. Now, when I teach this topic at a graduate level, I go into a subset of chemical equivalence that's called magnetic equivalence. That's even a greater level of sameness that becomes important in certain circumstances. But for the purpose of this course, I think we can just go ahead and say chemically equivalent protons are the same for our purposes. All right, let's take a look at some examples of chemically equivalent protons. So we'll take, for example, the two protons of diphenylmethane. The two protons of diphenylmethane are symmetrical. One's coming out of the blackboard, right? pH is just a benzene ring. One's coming out of the blackboard, one's going into the blackboard. They're interchangeable through a plane of symmetry through the plane of the blackboard. In other words, if I imagine the blackboard as a mirror plane, and I flip the hydrogens, the front hydrogen becomes the back hydrogen becomes the front. These are chemically equivalent. We talked before about stereochemical terminology and diastereotopic protons and so forth. These two protons are what we would call homotopic. If I change one phenyl group to a methyl group, these two protons are still interchangeable by a symmetry operation. They still flip, they still swap, and I get an identical structure if I flip them through the plane of the blackboard. In other words, they're chemically equivalent. In this case, we would describe these two protons topologically as enantiotopic. Remember, we discussed that concept when we described stereochemistry. And so a takeaway becomes that enantiotopic protons are chemically equivalent, and they don't split each other. Now, continuing to play with this idea, now I'll go to the molecule phenylalanine. Phenylalanine contains a stereocenter. Even if I don't draw the stereocenter, even if I don't draw any bonds, if I don't draw any wedges, if I just wrote the molecule as even if I just wrote the molecule like this carbon is a stereocenter. These two hydrogens now can't be exchanged by a symmetry operation because if I flip a mirror plane, I get the enantiomer of the molecule. In other words, these two hydrogens are diastereotopic. And they are therefore not chemically equivalent. And those two hydrogens would be diastereotopic even if they weren't immediately next to the stereocenter. In other words, if I added another methylene group here, and so instead of having a CH2 connecting to the phenyl group, I had a CH2 connecting to the phenyl group, they would still not be chemically equivalent. They might be closer to being coincident. They might behave as if they were chemically equivalent. If I had the stereocenter very far away, they would indeed, but topologically, they're not chemically equivalent. Eventually, as you're far enough from the stereocenter, as I said, they'll behave as if they're not chemically equivalent. They will appear at the same chemical shift, and they won't split each other. But they don't have to be right next to the same stereocenter, All right, rapid process. As I said, virtually every process involving rotation about sp3 bonds is rapid. So for example, in the molecule cyclohexane, we have hydrogens that are axial and hydrogens that are equatorial. And just for the sake of tagging them, I'll call one HA and one HB. And you'd say, wait a second, these two hydrogens aren't the same. They're not interchangeable by symmetry. One's axial, one's equatorial. But the ring flips rapidly. And so half the time HA sees itself as axial, half of the time HA sees itself as equatorial. Ditto for HB. HB half the time sees itself as equatorial, half the time it sees itself as axial. So HA, and because this is rapid at room temperature, the two protons, HA and HB, are chemically equivalent. If I cool down, the NMR time scale is such, and the Arrhenius or the Eyring equation is such that a process like this with a 10 kilocalorie per mole barrier or so is rapid at room temperature. But by the time you get to, say, negative 75 degrees, it's slow. And so if I cool down cyclohexane to negative 75 or negative 100 degrees, you will see separate peaks for the axial and the equatorial hydrogens, and they will split each other. But at room temperature, we see just one peak. Let's take a look at methyl cyclohexane. Methyl cyclohexane, again, we have the ability, we have hydrogens that are axial and hydrogens that are equatorial. And again, those hydrogens can interchange, but now there's a big difference. Because now, even though you have a rapid process, you have different environments, your equilibrium lies way in favor of the equatorial conformer. So HA doesn't see axial half the time and equatorial half the time, and HB doesn't see equatorial half the time and axial half the time. HA sees axial most of the time. HB sees equatorial most of the time. Put another way, HA is cis to the methyl group. HB is trans to the methyl group. So they see different environments. HA and HB are not chemically equivalent. All right, at this point, I'd like to talk about a molecule that's a little more complicated, and Stan is going to pass out the spectra of the molecule, or Stan and Sebastian will pass out the spectra of the molecule. They're double-sided. All right, so the molecule that's being passed out is phenylalanine, is a urea derivative of phenylalanine. It's urea derivative of phenylalanine methyl ester. And I'll put up the spectrum that you have.
Doesn't have a spectrum.
All right, so this allows us to begin to get our bearings on the NMR spectrum. And we talked about a little bit about where things are, chemical shifts in the NMR spectrum. This region here we call downfield. This region here we call upfield. In general, aromatic protons occur downfield. I said about 7 or 8 parts per million would be typical, but as I said, protons may go out of that range. So we've got lots and lots of benzene protons, 10 benzene protons here. These are our aromatic, our benzene protons. Well, if we're looking a little bit more at the spectrum, I said, well, plain vanilla methyl groups would be at about 0.9 parts per million, right? The plain alkyl region, not next to a benzene, not next to a carbonyl, not next to an electron withdrawing group, would be about 0.9 for methyl, 1.3 to 1.5 for methylene, 1.5 to 2 for methine. And I said that a beta substituent, I mentioned this again when we talked at the beginning of class, shifts you downfield by a couple of tenths of a ppm more. So it shouldn't surprise us that this triplet over here corresponds to this methyl group. And it shouldn't surprise us that the methoxy group, right, we said next to an electron withdrawing substituent is a couple of ppm further downfield than its normal position. In other words, instead of maybe 1 ppm or 0.9, we might be at about 3 ppm. Now, an ester group shifts you even a little bit further downfield, so it shouldn't surprise you that you see this methoxy group as a singlet at about 3.7 parts per million.
So,
I
didn't know that was like a singlet.
Well, I see a singlet sticking up, but this is a great opportunity to discuss integrals. So the area under a peak corresponds to the number of protons that are involved. And so you can measure the relative areas under the peak. And I think I'll slip my grid right under the spectrum because I want to mark on the spectrum. So you can go ahead and you can look at the rise in line here and see that height corresponds to the relative number of hydrogens. And so here, for something that I suspect is about 1 hydrogen, we have about 2.3 tick marks. My tick marks happen to be 1/10 of an inch. I could be using a ruler and measuring in millimeters. It would be some other number. And here we have about 2.3. And here we have, maybe it's about 12. And here we have, again, it's about 2.3, about 2.3. Here we have about 6. So it looks like it's about 2.3, not 6 hydrogens, rather 6 tick marks, 6/10 of an inch. So it looks like, right, if 6 marks is 3 hydrogens, and if 2.3 per hydrogen, it looks like, maybe I'm a little more, that looks closer to, looks like we're going up, it's hard staring into the light, looks like we're going up, that's about 7. So it looks like it's about 2.3 per hydrogen. In other words, this is a water peak here. This is 1 hydrogen, 1 hydrogen. This is 3 hydrogens, 1 hydrogen, 1 hydrogen. I'm not going to split up the aryl group right now. And then we get this group over here that collectively comes out to about 12 tick marks. Well, if it were a methyl group, we'd expect about 7 tick marks. So it's about 5 hydrogens, right? 2.3 goes into 12 about 5 times. So there's about 5 hydrogens here. And so we've got, and you can see this over here, we've got a methylene hiding underneath these hydrogens. So we've got our methyl group over here, but we've also got a CH2 group over here. Now, let's take a look at what we would expect for various hydrogens. So for this hydrogen here on the NH, we'd expect this to be a doublet. In other words, it has one neighboring hydrogen, right? It's got this hydrogen. And we see a doublet here. We see a doublet right over here at about 4.5 ppm. And so that's our NH group over here. Now this hydrogen is next to a heteroatom. This hydrogen here is next to a heteroatom. That's going to shift it down, right? A methine would be sort of 1.5 or 2. Next to a heteroatom is going to shift it downfield by a couple of ppm. Next to a carbonyl is going to shift it downfield by about a ppm. I'd expect this hydrogen to be pushing 5 ppm. And indeed, you see pushing 5 ppm, you see a peak that corresponds to this hydrogen. That peak ends up looking a lot like a quartet. It's being split, and I'll show you the expansion of it in just a moment. It's being split by 3 hydrogens, and I guess, and we'll see, all the coupling constants are pretty similar within about a Hertz. These 2 hydrogens are not chemically equivalent. They're being split by the methyl group. They're being split by each other. They're next to one heteroatom. These 2 hydrogens are the one that are buried underneath that methyl peak. So these 2 hydrogens here are basically in this range over here. And that brings us to each of these hydrogens. Each of these hydrogens is being split by each other. They're not chemically equivalent. And by a neighbor. They're being split with 2 unequal coupling constants. Each one appears as a doublet of doublets. And we'll take a look at those. Yeah.
So is it a doublet of doublets because they're being split by that one or that hydrogen, and they're being split by each other?
Yes, it is. So is it a doublet of doublets because they are being split by the alpha hydrogen and by each other, and those 2 coupling constants are unequal? The what's called geminal coupling constant, the one which they split each other, is very big, about 14 Hertz. The one in which they're split by this is a good deal smaller by the alpha protons, about 6 Hertz, and we'll get to analyze that in a second. So the way in which we analyze our coupling constants is to measure the difference between line positions. And I have an expansion on the next page, and I have some line listings. The line listings are pretty darn small. But you can see here, for example, we have the 3 lines that make up the triplet. So the peak I've sort of, because my pen isn't fine enough, the peak I've cut out is the water peak. I don't have an expansion of the triplet. But we have 3 lines in 13.67, 26.93, and 12.76, 1 to 2 to 1 height. It's centered at 1.06 ppm. And you can measure, we have the frequency of those lines in hertz. So here's our triplet. Our triplet consists of 3 lines, 538.90 hertz, 531.71 hertz. I'm just reading off the list. And 524.67 hertz are the positions of these lines. The distance between 2 adjacent lines is the J value. So now those J values are not, due to limitations of the instrument, they're not able to be measured exactly. So if we want to be as exact as possible, I'll average them. 538.90 minus 531.70 is 7.19 hertz. 531.71 minus 524.67 is 7.04 hertz. So we'll just take an average, the nearest tenth, because that's as accurate as you can get. We'll say this is a triplet, so we would say this is a triplet at 1.06 ppm, and we would describe it as triplet J equals 7.1 hertz, 3 hydrogens. That would be our description of the triplet. If we did the same for the doublet here, I did that already, it's at 4.50 ppm. It's a doublet, and J is equal to 7.8 hertz. And it integrates to 1 hydrogen. And you can go and analyze. If you really can't get much of an analysis, like I might not call, I would probably separate this into a singlet, but then I would probably describe this as a multiplet from, maybe I'd say 3.76. So I'd say 3.76 to 3.63 multiplet 2 hydrogens. But I want to take us at this point to our doublet of doublets and to discuss the analysis of it. So these guys here, it shouldn't surprise us, they're at about 3-ish, 2 point whatever ppm. They're a methylene. They're next to a benzene. They're beta to an electron withdrawing nitrogen that I've just erased. And so that pushes them downfield an extra ppm and a half or so, and they end up about 3 ppm. All right. Because they're close to each other, they are leaning into each other or tenting in what we call an ABX pattern. If they were far apart, you would see a pattern that looked very much like this. This is what you call a doublet of doublets. Because they're near to each other, you see them tenting in like so. You notice that tenting in. But the basic pattern is what we call a doublet of doublets. What's happening is you've got 1 hydrogen, so you've got a hydrogen here. It's being split by its neighbor and by this one with unequal coupling constants. This coupling happens to be big. This coupling happens to be smaller. And so what happens is the hydrogen sees 4 spin states. The adjacent hydrogen, the geminal, can be spin up or spin down. The vicinal hydrogen, the hydrogen that's 3 bonds away, can be spin up or spin down. And so you get splitting into 4 lines with a big J as that distance and a small j smaller j as that distance. Which means if we call our lines 1, 2, 3, 4, right? If we call these 1, 2, 3, 4, here's our pattern, right? 1, 2, 3, 4. The distance from 1 to 3 should be about the same as the distance from 2 to 4, and that's going to be our big J. And the distance from 1 to 2 is going to be about the same as the distance from 3 to 4. That's going to be our small j. And if we look on our peak printout, for our peak at 3.02 ppm, that's just right over here. It's the one that's these four. It's really hard staring into the light. It's these four over here. And if I transcribe my values in hertz, so this is our DD, our more downfield DD, 1470.58, 1463.94, 1456.82, and 1450.19. So those are our lines 1, 2, 3, and 4. Our distance from 1 to 3 is 13.76. Our distance from 2 to 4 should be identical. It's identical within the limits of a tenth of a ppm or a tenth of a hertz or so, 13.75. And here, our distance from 1 to 2 is 6.64 hertz, and here from 3 to 4, it's 6.63 hertz. So we would describe this peak as 3.02 DD, J equals, we report our big coupling first, 13.7, and then we, whoops, with a comma, report 6.6 hertz, and our integral was 1 hydrogen. If you do that for the other doublet of doublets, you will find the same J value within the limits of experimental error for the big J because coupling is mutual, but a slightly different J value for the other J for the smaller J because those two couplings to the methine proton are different. So in other words, whereas this peak is DDJ equals 13.8, 6 point, let's see, what did I say on that? Oops. I'm sorry, what did I do here? Oh, I copied the wrong numbers. That's 5.61. Oh, I know what I did. Oops. I did this. That's for the 2.92 ppm DD, so I'm just going to change that 2.92. And so coming back and finishing up here, this peak here at 3.03 is a DD J equals 13.7 hertz, 5.6 hertz. And this peak over here at 2.92 is a DD J equals 13.8 hertz, same value within the limits of experimental error, and 6.6 hertz, different value. All right, that sort of gives us a very quick analysis of what we'd call first-order coupling, a very quick description of first-order coupling. We've seen concepts of chemical shift come back. We've seen concepts of diet stereotopicity and chemical equivalence. And we've seen the notion of how protons that are the same split each other, or protons that are different split each other. Have a great Memorial Day weekend.